What does gerrymandering look like? Say you want to find out, by being as neutral as possible, how well a given map of congressional lines represents the will of the people. It's a tricky problem. Unlike statewide races for the Senate or White House where all the votes in a state are lumped together, votes for Congress are split across multiple districts. And how you draw those lines impacts who represents us in Congress. Judging whether these lines are seriously out of whack or gerrymandered takes more than just comparing the vote totals to the representatives sent to Washington. And gerrymandered districts aren't always monster-shaped, like the practice's namesake in 1812 Massachusetts, or Jerry here. You need some way to account for all the complications of geography and the rural-urban divide and other factors. You need a benchmark of what's normal, a measurement.
If you didn't know how much the thing weighed beforehand, how are you going to ever decide if someone had their finger on the scale and pushing it down?
That's exactly what a team of Duke mathematicians set out to do. Their methods worked so well that a 3-judge panel used their research as justification for overturning maps redrawn by Republicans in 2016, calling them unconstitutional partisan gerrymanders. One way to figure out how normal something is, whether it's the roll of a die or an election, is to simulate it over and over under different conditions. Every roll of the die gives you a result. Count those results, and you get a distribution like this. But if you want to simulate an election with small changes in how the maps are drawn, you need a lot of maps. All of them built out of North Carolina's almost 3,000 voting precincts. And given that there are more ways to combine those precincts than atoms in the universe, that's way too many to draw by hand. Enter the machine. The Duke team used a formula called a Markov chain Monte Carlo algorithm to rapidly draw 150,000 versions of North Carolina congressional maps based on slightly shifting the lines drawn by Republicans in 2012 and 2016. The team also used a map created by a bipartisan group of retired judges who sought to simulate what an independent redistricting commission might look like.
We do this hundreds and hundreds of thousands of times. And what that does is that slowly makes the boundaries evolve and move around. And that is the essence of a Markov chain Monte Carlo algorithm.
After booting the maps that weren't compact or contiguous or didn't follow the Voting Rights Act, researchers were left with more than 24,000 maps. Then they tallied the votes and looked at the number of Democrats elected in each map in both the 2012 and the 2016 elections.
I can say, well, what outcome did I see the most often? Or what were the outcomes that I saw often? And more importantly, maybe, which outcomes did I barely ever see?
That distribution looks something like this. Toward the left, you see how the maps actually performed in 2016. 3 Democrats and 10 Republicans.
Turns out if you look at it, you almost never see the outcomes that our current maps produce. Our current maps are outliers.
Out of all the 24,000 plus simulated elections, this outcome happened only about 160 times. A fraction of a percent. In more than half of the simulations of the 2016 election, North Carolina would see 5 Democrats and 8 Republicans elected. That's pretty interesting. But the Duke team went further, exploring measures of packing and cracking voters often employed in the worst gerrymanders. The 2 techniques dilute voting power, either by loading up voters of rival parties in one district or breaking them apart into many districts. Of course, some districts are expected to be more Republican or Democratic than others. Politics is regional, after all. And you can see that if you plot the simulated election districts from most Republican to most Democratic. But when you add in where the 2016 maps fall, it's almost always on the extreme edges. That means the map packs way more Democrats in blue districts and cracks them between more Republican-leaning districts than the bulk of the simulations.
We almost never saw districts that had that few Democrats in them. So this gives some evidence that, in fact, what happened in this map was that Democrats were removed from the competitive districts and moved to the uncompetitive districts.
Based on these simulations, the 2016 map certainly produced an unlikely outcome. But it wasn't an impossible one. The maps could have yielded 3 Democrats and 10 Republicans purely by chance. So the Duke team tested that too. By slightly redrawing the Republican-drawn maps to swap voting precincts between the districts, the researchers were able to examine whether small changes drastically altered the election outcomes.
If you do that, you see that they become much less gerrymandered. The minute you start moving the boundaries a little bit, it's very fragile. They become less gerrymandered.
The results in these shifts were more favorable to Democrats to a large degree, raising the suggestion that the lines were precisely engineered for the benefit of the GOP. The research resonated with federal judges, who said it provides strong evidence that the General Assembly intended to subordinate the interest of non-Republican voters and entrench the Republican Party in power. Republicans, however, disagreed and objected to assumptions in the research that voters vote for party rather than person. They also said the maps ignore the many implicit criteria they use when drawing maps in the General Assembly, which they never articulated. GOP defendants maintained that their maps are fair and legal, and successfully argued that the U.S. Supreme Court put the case on hold. That means our current maps are likely to stay in place through the 2018 election. The High Court will eventually make calls on partisan gerrymandering cases in Wisconsin and Maryland, with a possibility of more states to come. For WRAL News, I'm Tyler Dukes.